H4NO3, this one is a bit more complicated because not everything occurs on the charts, the charts that we have. And so we can take a look at this together or separately. We'll look at it separately in terms of ions. We'll look at the individual ions and see what the properties are for these ions. So we have the ammonium ion and the nitrate ion. Now, normally when I do these, I go on a certain sequence. I usually do, let's say, metathesis first. And then I go to acid-base, and then I go to redox. Just because metathesis reactions are quite common, and it's good to knock those out first. And so let's take a look at these two in terms of metathesis. Since the metathesis overlaps with acid-base, we can hold off on the acid-base since we're going to look at acid-base reactions as well. And so right now we're just looking not at the acids chart, we're just looking at what anions like, let's say, ammonium, and what cations like nitrate. And as far as that goes, we're looking for either precipitates or gas formers. And gas formers would be, I don't know if I talked about these, but these would be acid-base ones. Like, for example, H plus like carbonate. If I had two H pluses going to a carbonate, that forms H2O liquid and CO2 gas. It forms carbonic acid. H2CO3 is pretty unstable. And so we can put that in quotation marks and it just spontaneously decomposes. But this is acid-base. In fact, all the gas former reactions are acid-base. And so there's overlap there. But I don't really treat those separately. Really, when we're looking at this, we're looking at precipitation reactions in metathesis. So as far as precipitation reactions go, ammonium. Group 1 and ammonium are all soluble. Right? So since group 1 and ammonium are all soluble, we don't expect anything to happen there. So ammonium, all soluble. Therefore, in terms of metathesis, there's very little reaction other than acid-base, But acid-base we're going to look at in the next step. And so it's the way to do it. Well, ammonium is not very reactive. What about nitrate? Is nitrate very reactive in metathesis? Then we think about the solubility rules for nitrates. Nitrates, chlorates, and acetates are all soluble. So nitrates are all soluble as well. Now, is nitrate much of a base? No. And so we leave metathesis here, so no reaction for metathesis. No matter what I mix it with, I can mix it with sodium carbonate, nothing's going to happen. I could mix it with iron 3 phosphate, nothing's going to happen. No matter what other ionic compound I choose to mix it with, that's not an acid-base reaction, nothing will happen. Okay, so metathesis is unreactive. So then I move on to acid-base, and here we're going to look at Bronsted acid-base. So ammonium, we find that on the chart. Some things occur on both sides of the chart, like ammonia. Ammonia you find on the acid side and the base side. It's a better base than it is an acid, but it's on both sides. That's what we call amphoteric. Ammonium, however, is not on both sides. Ammonium is only on the acid side. And so ammonium is a weak acid. And so it doesn't react with all bases. It has to be strong enough. The base has to be stronger than what? NH3, right. And so weak acid reacts with all bases stronger than NH3. How about nitrate? is a base, but what do you know about this particular base? Yeah, but there's nothing really stronger than water, you know, as far as base goes. I mean, stronger than, oh, acid's stronger than, actually, it's such a weak base, you know. When we look at the acid chart and the leveling effect here, that there's no reaction. It's so weak. And so this is the base, but too weak to react in water, or just too weak to react. So you aren't going to neutralize any acids. This is like the question I asked you earlier. If you ran out of antacid, can you substitute table salt for antacid? You know, well, chloride's a base, just like nitrate's a base, but is chloride going to be neutralizing, or table salt going to be neutralizing any stomach acid? No, not at all. So it's the same situation. And then we move on to redox. Nitrate's okay. You know, when I look at the chart, I see that nitrate's on there. Nitrate's an oxidizer. And it's a moderately strong oxidizer. In combination with H+, can gain electrons to form NO plus 2H12 liquid. NO's gas. So this equation is right off the chart here. And so it's a pretty good oxidizer. Nitrate's a good oxidizer. But we need H+. Do we have H+ present? And the answer is actually we do have H+ present. It's not in the form of H+, it's in the form of what? Ammonium. Yeah, ammonium is going to supply the H+. Because ammonium is an acid, and acids generate. It's not going to supply a large amount of H+, but it supplies enough H+ to allow it to react. So we have a good oxidizer. Now, ammonium's not on the chart, though. What are the redox properties for ammonium? And so this is not on the chart. So it means a couple of things. One, if it's not on the chart, then it's not significant. That is, it doesn't really have very strong redox properties one way or the other. Or two, it does have good redox properties. There's just not enough room to include it in the chart. And so to figure that out, you should look at the oxidation states. Oxidation states should give us some clue as to what, you know, if it has a high oxidation state, one way or the other, positive or negative, then it's likely to be more reactive than something kind of in the middle, you know, of the range. And so not on the chart, we have to figure it out. So first thing we look, is it electron rich or electron poor? Electron poor because of the positive charge? Well, we can't look at the net charge. What is it? Nitrogen's a +3? Well, it's winner take all. And if there's a struggle for electrons between nitrogen and hydrogen, who wins? Yeah, nitrogen's more electronegative. Nitrogen, oxygen, and fluorine are the three most electronegative elements on the periodic table. And so nitrogen takes all of them. That means nitrogen with 0 electrons. How many is nitrogen supposed to have? Oh, actually, nitrogen takes all of them. It doesn't get 0 electrons, it gets all the electrons. How many is all the electrons? 8. So nitrogen ends up with 8, hydrogen ends up with nothing, and it's supposed to have 5. And so the oxidation state of nitrogen is -3. It's -3 because it has 3 extra electrons. Hydrogen's at a +1, but that's nothing unusual for hydrogen. -3 on nitrogen is more significant. What end of the spectrum is that? Is that on the electron-rich end or the electron-poor end of the spectrum? Electron-rich. In fact, nitrogen oxidation state varies from +5, losing all 5 valence electrons, to -3, gaining 3 extra electrons to complete the octet. And so -3. And therefore, you would call ammonium electron-poor or electron-rich? Electron-rich. And electron-rich species are fuels. And so ammonium salts are combustible. You know, we can burn this stuff. Like, can you burn sodium chloride? No, so burning sodium chloride would be awfully difficult to do because chloride's not a very rich, electron-rich species, and sodium certainly isn't. But ammonium salts can be. This is weird because what is the formal charge on nitrogen? The formal charge on nitrogen is plus. The oxidation state on nitrogen is -3. So it's a bit weird. But we look at the numbers differently. And so what would you say about ammonium? Well, you would say it's electron-rich, and electron-rich species are good. Just the opposite, good reducers, right? This is electron-rich. Looking at the formal charge, though, it certainly does not look electron-rich. This is electron-rich, and it's going to be a good reducer. Oops. All right. So this is why I showed the videos the other day. This is what makes ammonium nitrate a scary substance. It's a scary substance because on the one hand, if we look at nitrate, why is this a good oxidizer? Nitrate a good oxidizer? Because it's electron poor. Why is the nitrate electron poor? Let's take a look at the oxidation states. What are the oxidation states here? Well, nitrogen versus oxygen, who wins in this case? Oxygen. Oxygen's more electronegative, so it's going to take all the electrons, leaving nitrogen with no electrons. So if nitrogen loses all its electrons, what is it? Plus 5. Oxygen's -2. Oxygen's going to be happy at -2. So the reason this is scary is because one of these nitrogens here is rich at -3. The other nitrogen here is poor at +5. And so one of the things you can say about ammonium nitrate is it is an unstable situation. You know, an unstable situation is this, you know, if the two nitrogens got in a tug of war, which one's going to win? You know, they're both kind of even in a sense. And so you would expect it to go, you know, you'd expect the rich nitrogen to lose some and the poor nitrogen to gain some. However, that doesn't happen, you know, because it's a solid. In a solid, each ion has a lattice position, and they can just vibrate in those lattice positions. They don't react with one another unless it gets hot. If it gets hot, then the kinetic energy increases and the motion increases. And so you're going to get more violent vibrations, which can result in a reaction that occurs. And so if you were to heat this up, you have potential for a big explosion. In fact, we saw the explosion in China. It's huge. Explosion in Beirut, which I didn't show the video for, but that was huge also. Enormous explosion in Beirut. And then the explosion in Texas City. You know, all those, what they have in common? They're all ammonium nitrate explosions. Oklahoma City too, ammonium nitrate. So that would be it. That would be the analysis, you know, as far as chemical properties go, and that way we can try to get a feel for it. Now, how strong is a reducer? Where do we place it in the chart? That I don't know. We have to kind of guess at that. But you know, the guess would be that this would be a pretty decent reducer, pretty good reducer. And then from the visual evidence that you've seen, that is from the explosions, then you can say, yes, it's got to be a great reducer, because otherwise you wouldn't have those massive explosions occur. And so that's our kind of our mix of, like I said before, it's a two-pronged approach. It's a mix of theoretical and, you know, observational, empirical observation. So the theoretical part is, well, we know that this doesn't look great, but how bad is it? You know, is it not? Well, maybe it's not that bad. You know, maybe it's not that reactive. But then when you mix that with, you know, the observations of the explosions, then you go, wow, that is really unstable. This stuff is just on the verge of having a massive explosion, kind of thing. You know? But then, that's on the one hand. Then on the other hand, hey, this stuff is used as fertilizer. So it's got to be stable enough so the farmers can spread it over their fields, you know, without worrying. You know, if the farmer's scooping it up and spreading it over the field, they probably aren't worrying about a massive explosion, you know, that's going to blow them to pieces, you know. And so it's just that. But, you know, something like this, you got to worry. If you scoop it too hard, you know, you get that impact which pushes the ammonium and the nitrates together, maybe it can start something. And so there are compounds that are touch sensitive. You know, there's one, I should show maybe on the video, there's one that's so unstable that there's a demo where they float a feather. So there's a feather floating down, and then it touches the surface and it explodes. You know, it just caused that one little displacement of ions, or one little displacement of something, and then it just went off. Whereas, you know, for example, the thermite, did I show you the video of the thermite? Did you see the car blow up? You didn't? I didn't show the video of thermite? All right, let me show you the video of thermite. Let's take a look at this now. Thermite is just powdered aluminum. You know, powdered aluminum is much more dangerous than a chunk of aluminum or bar of aluminum. Why? Because of the surface area. You know, when you have powdered, like powdered flour, did I show you the grain silo bakery explosions? No, I didn't show you that either? Okay. You know, powdered metals are electron rich, but, you know, they don't seem all that flammable. I mean, this thing's made out of aluminum here, this tray. Well, I'm not worried about this catching on fire. However, if you buy powdered aluminum, it's marked flammable, you know, potential fire or potential explosion even. It depends. It's like if you have a bag of flour, let's say you have a 5-pound or 10-pound bag of flour, it's pretty hard to catch on fire, right? However, you know, in bakeries, you might create a 10-pound aerosol of flour. So the flour goes up in this big cloud of dust. And this big cloud of flour dust mixes with the air. And you get the right mixture so that if there's a spark or a hot surface, it ignites and either burns rapidly or it explodes. You get the detonation. And so there's bakeries that have had massive explosions when that dust cloud hits light fixtures, hot light fixtures, causes an explosion. Grain silos and whatnot. But thermite is you just take powdered aluminum and mix it with powdered rust. The powdered helps it react faster. You know. Okay, so aluminum we already know this is electron rich. It's a pretty good reducer. What about rust? What do you know about rust? Well, rust isn't in our chart, but one of the pieces is in our chart. And one of the pieces that's in our chart is iron 3. Iron 3 is a pretty good oxidizer. In fact, iron 3 is very close to nitrate and H+. So it's a pretty decent oxidizer. Oxide What do you think about oxide's not on the chart, but we know we've seen oxygen in the -2 oxidation state before in water, in other things, and it's pretty stable. So oxide's not a big deal, but the iron 3 is a decent oxidizer. Aluminum is a good reducer. But this reaction is very slow. Why is the reaction very slow? Because these are solids. You know, the only way you can get them to react is to grind them together or heat them up. If you grind them together, then maybe you can get the reaction started. You know? And so that's what some people might do, is they grind together, and you might get a redox. Or you heat it up. Now, if you can heat it hot enough to melt the aluminum, then you have molten aluminum. And liquid aluminum can react quickly with a solid. But if you have a solid, it's metastable. You know, this doesn't seem very reactive, does it? Like if you accidentally have rust in contact with aluminum, does that seem like very reactive? No. It isn't. Until it gets hot. So we can take a look at this reaction. So this is the part, you know, we kind of analyze this, look at the oxidation states. Oxidation state on aluminum is 0. Oxidation state on iron is +3. You know, to get some kind of idea. And then we see how things react.
From the sheer volume of emails we receive every week, it is clear that you are obsessed with thermite, the fiery substance that's hotter than a blaze in a chili factory. I've got another new request here. It's from Jordan Baxter, age 10, of Somerset.
First, in a water thermite, the fibers in place on a carbonate and see if it burns into the ground.
Okay. This is thermite. It's a powdered mixture of iron oxide and aluminium, which, when ignited, burns at 2,500 degrees Celsius, which is very, very hot. This is a colour. It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The engine block is the densest part of the car. It's basically a huge lump of metal, and, well, it's very hard to melt. Lucky then, the brainiacs have plenty of thermite, especially packed into the slow-release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Within seconds, the fiery concoction eats through the bonnet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory of thermite. A quick check confirms a clear path of destruction through the engine. So, there you go, Jordan. Thanks to thermite, this car's driving days are well and truly over.
Okay, this is part 2 to look at.
We have received hundreds of your letters a week. He says, okay.
You start a thermite reaction on top of it and let it burn through to a full petrol tank.
Well, I don't know, but I've got just the car for it. So let's find out. This is thermite. It's a powdered mixture of iron oxide and aluminium, which burns at 2,500 degrees Celsius, which is very, very hot. This is a car that was not until last week when we got its first taste of the awesome power of thermite. Now that the engine is running the roof directly above the fuel tank, the topper, and just 4 feet of covering car stands between the thermite and 8 gallons of petrol. Like the touch paper and stand well back. The irreversible thermite reaction begins. Thermite produces a stream of molten iron which melts through the car in seconds. It's 2,500 degree heat igniting the expanding petrol in a devastating fire, leaving behind a car that won't be going very far anytime soon. So there you go, Ryan. Can thermite make your car explode? And yeah.
Okay, so that was a thermite there. You can kind of get an idea. You know, this is a pretty good reducer. This is a pretty good oxidizer. Not the greatest, not the strongest. If we had even stronger oxidizers and stronger reducers, we would expect even more violent reactions than that. So, speaking of reactions, you might want to get a lab coat. You know, I had a question about a little bit more expensive coat. You know, the cheapest was like $15, and that's what I have, but they're nicer coats. If you want a nicer coat, you probably want something with some flame, resistance, that is fire resistance. So when I was at UCLA, they made all the organic chemistry students buy 100% cotton lab coat. At the time, it was pretty expensive, $70 or something. But now, look, it's 100% cotton one, $27. A little bit more expensive, but will have better flame resistance than mine. Mine is synthetic. Actually, the one I had at UCLA was a little heavier weight. So it's more like this. But still, this is a pretty good price. This 7-ounce cotton, 100%. So good flame resistance. If you want really good flame resistance, you go with the Nomex, or some other fireproof material. Firefighters use, but that's going to be around $100. But it depends on what types of materials you use. They're now requiring this for all, I think, chem students to wear a lab coat. It used to be just the organic chemistry students, but they had a very serious accident at UCLA. Did you hear about that? There's not a UCLA graduate, but another person who just graduated. I forgot from which school, but they were going to take a gap year, work for 1 year, and then start medical school, I think, the year after. I think they might have already been accepted to medical school. So this person was working in a lab, and in this lab, they were working with air-sensitive materials. A lot of these air-sensitive materials are very electron-rich. I mean, way more than aluminum. If you have some powdered aluminum, are you going to worry about it catching fire spontaneously? No, we don't worry about it. But the materials that we work with, the air-sensitive materials, are such powerful reducers. Just the oxygen in the air, once it comes into contact with the material, it'll spontaneously catch on fire. No heat, no touch paper, no nothing. Just expose it to air, and then it erupts in a fireball. Those are called pyrophoric materials. I used to work with lots of pyrophoric materials. Pyrophoric materials are these powerful reducers, and not only air, which has oxygen, 20% oxygen, 21% oxygen, which oxygen is a pretty good reducer. Not just air, water too. Is water a very good oxidizer? No, water is a pretty poor oxidizer. And these pyrophoric materials could react very violently with water as well. So you don't want any water, you don't want any oxygen. And so I used to work in a box that's called a dry box. It looks like the hood there. It's just a solid box. And then you have gloves that go in. And inside the box, you change the atmosphere. So inside my glove box, I had argon gas, which is noble gas, filled. And so there's no oxygen and no water. Otherwise, my stuff would decompose. Well, it depends on what you're doing. If you're just doing small scale stuff, and sometimes working with a glove box is such a hassle. And so what some people do is and I did this too, you work with standard glassware like this, but you have caps that go on here, and these caps are airtight. In the caps, it's metal, and then in the middle of it, there's a rubber septum. And the rubber septum, you can poke needles in. So, for example, if I had some air-sensitive material in here, I'd poke 2 needles in there. One needle, I'd use nitrogen's cheap. Argon's kind of expensive. So I'd purge this with nitrogen, dry nitrogen. No O2, no water. And then it'd go in the inlet needle, and it'd purge the air out the outlet needle. So I just purged this until I thought I got rid of all the air. Okay, then pull the needles out, and then I have this. My sample in a inert atmosphere. Inert nitrogen is what they call pseudo-inert gas. Nitrogen has a nitrogen-nitrogen triple bond. It takes about 1,000 kilojoules per mole to break that. And so it's very strong. So it's pseudo-inert. It's hard to get nitrogen to react, but there are some metals it reacts with violently. So for example, lithium, you form lithium nitride. It's not a good mixture because nitrogen can be an oxidizer as well. But for the types of things I was doing, it wasn't reactive in that way, but I was still working with some powerful reducers. It depends on the mechanism, the redox. So anyway, this student was doing the same thing, I don't know if they were using nitrogen or what, but they had a rubber septum on there, and they wanted to transfer, I think, about 20 milliliters of pyrophoric material from one container to another. So they poked this needle in there with a syringe, and then draw the liquid up in the syringe, and then move it over and then poke it into another vessel and then squirt it in there. This other vessel would have to be filled with nitrogen or argon or something like that. Argon's very nice. Argon's very nice because it sinks. Argon is more dense than air, so it sinks to the bottom and then pushes the air up. So I've always liked argon. Helium's more of a hassle, because helium is much lighter than air, and helium leaks out like balloons. Helium balloons, helium leaks out of that balloon quickly. The same thing with containers like this, helium leaks out. In glove boxes, a lot of people used to use helium, but helium, the price has skyrocketed, so nobody, I think, uses helium anymore. Well, anyway, this person, was going to transfer 20 milliliters. So if you're going to transfer it in a syringe, you probably want to use a 40 milliliter syringe or something like that, right? 40 milliliter syringe gives you some room to play, but apparently this person used like a 20 milliliter syringe or 25 milliliter syringe. So it was already at max capacity. When you're already at max capacity, it's so easy to accidentally pull the plunger all the way out, and then that exposes all the material. Or it's so hard, you don't want to pull it out a little bit or pull it in. It's so hard because it's at max capacity, because 20 milliliters is quite a lot. And if that's pyrophoric material, that's very dangerous, because that could result in a pretty big fireball. Well, anyway, apparently the person used a syringe that's too small, like 20 or 25 milliliter, pulled it out, and then it started squirting liquid. Well, as it starts squirting liquid, that liquid immediately catches on fire, so it's a little flamethrower. And so they had a little flamethrower going on, and then the person was wearing a flammable sweater. It's made out of some flammable material, and the sweater caught on fire, and then the rest of the clothes caught on fire. If the clothes catches on fire, the thing you want to do is, run over here to the shower, right, and drench the flames. I'm not sure the sequence of events that happened, but I think they were working alone as well. You're not supposed to work alone in lab in case something like that happens and you need help to get there. But end result was they suffered 2nd and 3rd degree burns, and I think they were able to survive for another week, and then they passed away from the burns. So that was just a brand new graduate from, and then something like this is when I read this, I thought, oh, that's just tragic because, you know, something like this you could train people how to work safely with dangerous materials. You know, because I worked with a lot of dangerous materials. This is even before I graduated from UCLA. I was working with high pressure liquid fluorine gas. You know, that was very dangerous because fluorine is, you know, the most powerful oxidizer on the chart. Did I tell you when I noticed the leak? No? Yeah? All right. I think I did. I thought I did. Well, anyway, that's dangerous stuff. It was like this. You know, this is what we're doing in chemistry. We're learning, you know, skills to handle things that are potentially hazardous safely. You know, that's what we're trying to do. You know, it's like this whole the whole lockdown stuff. You know, initially when they're talking about locking down the labs, I thought, why? You know, this is our business. Our business is to be able to deal with hazardous substances. Okay, if there's a virus, then we should have protective equipment like an N95 mask, goggles, gloves, you know, distancing. And then this room, you know, the lab room, you know, we have this fancy air filter here, but I have mixed feelings about this. You know, this is not only does it HEPA, but this is UV and other things built into it. This is a really impressive piece of tech. But, you know, is it really necessary? But because in this room, you know, as I recall, we have 5 room changes per hour. That means in every hour, the old air is flushed out, new air is flushed in 5 times per hour. And so we're constantly getting fresh air in here, although it doesn't feel like it. Maybe it's way down, you know. But I think you'll know when it's pretty up because you pull this and it's pretty well balanced. But you hear that suction? You know, that suction is continuous. And we have alarms here. This is, right now, this is about 100 feet per minute. You know, that's blowing in there. Sometimes, some of the labs I worked in, the suction was so intense you couldn't open the door. This is like a vacuum. You had to really pull hard to open the door because there's negative pressure in the lab, positive pressure outside, you know, so it's like a vacuum in here, and pulling the door open so hard because air is being sucked in here, flushed out. So I thought with all the room changes, you know, and with N95, which, you know, at the time, you know, the state of California had purchased $1 billion worth of N95 masks at that time. So I thought there should be plenty of masks to go around to give everybody an N95, you know, in lab. So I was thinking we could do it, you know. There's risky stuff that people do all the time. Like there's some people I know that don't drive. They don't drive because, you know, it's risky. They don't want to subject themselves to that kind of risk driving. And they say flying an airplane is safer than driving. They don't fly an airplane either. But then so, you know, there's some people who shouldn't be dealing with chemicals that are dangerous like this, you know, because it is quite a big risk. You could, you know, did I ever show you the fluorine chemist handshake? When I started fluorine chemistry, my advisor over there, he showed me the fluorine chemist handshake. And he said, okay, when you start off as a new fluorine chemist, you go to the conference and you meet people. You know, hey, how are you doing? You know? And then the next year you're there, you go, hey, how's it going? You know? And then the next year you're there, oh, yeah, good to see you, you know? And then you have to retire once you lose all your fingers. So maybe a fluorine chemist only has a good 5 years or so, 4 years before they have to retire, depending on how many fingers they blow off. There was another lab where they worked with reactive chemicals, and the other lab they worked with reactive chemicals was located on the roof of the chemistry building at UCLA. So in case the lab blew up, it didn't really damage the floor. You know, things could go on, but you know they're well aware of the risk of that. And so what we're doing is we're just trying to get a feel, you know, through a mix of theoretical analysis, that is oxidation states, and empirical analysis, you know, how these things react, get a feel for their reactivity. So I was really scared of working with fluorine, you know, when I first started. Really thought I was going to die, potentially. But I started reading about fluorine. You know, then I thought, maybe it's not that bad. You know, maybe it's not at the top, the very, very top. I'd read this one study where they got a group of Army volunteers. And the Army volunteers were given a glass jar with a lid. And they were told to take the glass jar and the lid and walk into a fluorine cloud, or as deep as they can go. And then once they couldn't tolerate it anymore, to seal the lid on the jar. And then they could take it out, and then they could analyze, you know, well, what was the concentration of fluorine gas that could be tolerated by a human. You know, these were all gung-ho volunteers who wanted to do that. And so after I read about that and they didn't die, then I thought, maybe it's okay. Kind of like chlorine, you know. Chlorine is another strong oxidizer. All right, does that answer the question about that then? So this is the reason I worded it like this is because also while I was a student at UCLA, I had an oral examination. This is getting my oral examinations are very rare, say, you know, or if you're undergrad getting your bachelor's, it's pretty rare to have an oral examination, but I had an oral examination. One of the questions I got asked was, what are the chemical properties of phosphate? What are the chemical properties of phosphate? And then think back to like Chem 1A or Chem 4. And you got to think in terms of, okay, double replacement, single replacement. I knew double replacement. I knew single replacement. I knew combustion reactions. I knew precipitation. I knew neutralization. And so how do you answer a question like that thinking, okay, it doesn't fit the double replacement form. It doesn't fit the single replacement form. It's not a combustion reaction. You know, all I could say was, you know, phosphates used in detergents. You know, I know laundry detergents, a lot of them have phosphates in there. It's pretty basic. You know, I think I said, yeah, it's pretty basic. It's like a moderate base. It's right below sodium hydroxide. Not on our base chart, but on another base chart is right there. So it's a moderately strong, weak base. And that was it. I had to think about it quite a lot. And so there's a lot of dead, you know, what they call dead air. Dead air is like nobody's talking, but everybody's waiting. I was supposed to be the one that was talking. And that really got me thinking, you know, do I really know chemistry? I mean, chemistry is like, isn't chemistry and chemists supposed to be dealing with chemical properties? You know? Any other questions? All right, but you know, when we did this, we didn't cover all bases. One thing I skipped was Lewis acids and bases. I did Bronsted. Why did I do Bronsted? Probably because Bronsted's easy compared to Lewis. You know, Lewis is more difficult. But the problem is Bronsted is not the entire universe of acid-base reactions. The entire universe of acid-base reactions is Lewis. Lewis encompasses in all acid-base reactions. Where did I leave off last time? Did I leave off with ethylene diamine tetraacetate? Acetate, yeah. You know, that's what we're starting talking about Lewis acid-base reactions. So let me just add this. Lewis acid-base reactions would be all of them. You know, Lewis acid is electron pair acceptor. Lewis base is electron pair donor. So what constitutes, a lot of different things constitute electron pair acceptors and electron pair donors as well. But anyway, this is the universe of acid-base. So we call this the acid-base universe. In the acid-base universe, we have a galaxy, let's say, and this galaxy is the Bronsted acid-base, or I guess we could say galaxy or whatever. So in this, we have some Bronsted. And then in there, we have the, like the star, you know, the Arrhenius acid-base star. Arrhenius is so limited. So if you think of the forest of acid-base reactions, Lewis is the entire forest. Arrhenius would be just like a single tree in that forest. Bronsted would be like a patch of trees. Pretty significant, but still not complete. So there are some things that are just kind of weird, you know, that you wouldn't expect to be an acid. Let's say here, Ca2+. Does that look like an acid to you? No, but you know, it's an acid. It's a Lewis acid. It's capable of accepting electron pair. We'll look at it later. Pb2+, you know, that's an acid. You know, there's some things that you might think are bases. Like, okay, so these would be Lewis acids. But there are lots of other things, you know. CO2. Does that look like an acid to you? Yeah, it doesn't look like an acid to me because I'm used to Bronsted, but you know what? This is also a Lewis acid. So in the Lewis acid base universe, we're going to look at these metal cations as acids. And if we look at metal cations, in fact, I'm going to call it transition metal, but they don't have to be transition metals. Like calcium is not a transition metal. But we're going to take another, let's say, part of the universe, which would be, let's say, some galaxy here. This is going to be what we're going to call the transition metal complexes. The transition metal complexes aren't Bronsted at all, but they aren't CO2. They're just metal cations. And metal cations can be electron pair acceptors. Okay, and then then there are the bases. Bases might be like your standard base. You know, some bases are the same. So for example, ammonia. Now, when we look at ammonia, what do you think? Yeah, that's a Bronsted base. It's a proton acceptor. But this one's also a Lewis base because it has a lone pair like this. And that lone pair can be donated to a Lewis acid. And so in the Lewis acid base reaction, what we have is this. And the jargon goes like this. The base attacks the acid. So the ammonia attacks the acid. Let's say it likes lead better. In fact, it does like lead better. Because lead would be a better Lewis acid than calcium. But is there a chart that shows me that? No. And yes and no. You know, the nice thing about Bronsted is we got this nice, clean acid-base chart. You know, the strongest acid HCl4, the weakest acid ammonia, or no, methane. Strongest base methide, weakest base perchlorate. And so we got the nice acid-base chart, but those are only for Bronsted. For Lewis, we don't have an equivalent. You know, if we limit ourselves to this, you know, this galaxy, the transition metal complexes, then there are some patterns in reactivity that we can see. This would be a Lewis base. And so let's take a look at characteristics that make a good Lewis base, because that might be easier to see right now. A Lewis base, we have to have an electron pair, a lone pair. And not only that, this nitrogen has to be delta minus, like that. And so that would make a good Lewis base. Like that. This would be ammonia. And so ammonia is both a good Lewis base and a good Bronsted base. There are others that are similar to ammonia, and we'll talk about these right now, the amines. The amines are ammonia-like compounds. So for example, if we take one of the hydrogens off and put it in CH3 instead, which is called a methyl, and there's still a lone pair on that nitrogen here. And so now we have a carbon bonded to the nitrogen instead of a hydrogen. So we have two hydrogens and a carbon. This carbon's going to have three hydrogens bonded to it. So that's a methyl, and we'll still have the lone pair here. Now, what's the electronegativity of carbon? Do you know? Close, 2.5. 2.5 is electronegativity of carbon. What's the electronegativity of hydrogen? 2.1. Now, 2.5 and 2.1 don't seem all that close, but we said they're close. 2.5 is close to 2.1. And so, by changing from hydrogen to carbon, it really didn't change the electron cloud that much. In other words, the delta minus is still, nitrogen's more electronegative than both hydrogen and carbon, and it's going to pull the electron density away. Carbon is going to fight it, though, a little bit, you know, in that sense, a little bit more than hydrogen. But then this carbon's electron rich, as is, so it doesn't really have to fight it. In fact, when we look at this carbon, what is the oxidation state on that carbon? Okay, well, it's going to win all these. 2, 4, 6, loses this. It's supposed to have 4, minus 2 is correct. And so it's fairly rich. You know? It's not the richest, but it's fairly rich. And so what happens is this. Ammonia, and this is called methyl because this CH3 is called methyl, and it's ammonia-like, so it's called methylamine. Ammonia and methylamine are about the same in terms of basicity. We can do this again. Let's pull off another hydrogen. So if I pull off another hydrogen, I'm going to have, let's put 2 methyl groups on here. And so I'm going to replace 2 of the hydrogens with carbons. And that's not going to change things that much either. Because hydrogen and carbon are roughly the same. And so all these are going to have about the same negative. You want negative charge. The more negative charge you have, the better it's going to be at donating electron density. or the pair of electrons. This is called dimethylamine. And so dimethylamine, methylamine, and ammonia are all about the same. So let's get rid of that last hydrogen. If we get rid of that last hydrogen, we make this. And this is trimethylamine. There are no hydrogens on here, so in a way it doesn't look like ammonia at all, but in another way it's just like ammonia because it's got a delta minus on the nitrogen and a lone pair. So all these are amines here. One time I had to order some ammonia, NH3. And so I was looking in the catalog and I couldn't find any ammonia. You know, I couldn't find any ammonia because they called it something else. It was the European catalog. They didn't call it ammonia. They called it by another name. You know, how would you name ammonia using the systematic nomenclature system? What would it be named? It's a binary molecular compound, so you learn about binary molecular compounds like CO2. CO2 is a binary molecular compound. We call it carbon dioxide. Right? And so what would you call ammonia as a binary molecular? Yeah, nitrogen trihydride. So I couldn't find the ammonia because, you know, they had called it nitrogen trihydride. But once I saw the formula for nitrogen trihydride, well, then I knew it's ammonia, and I just ordered some nitrogen trihydride. I needed some for some base properties, some weak Bronsted base, that is. What about this? NF3. What would you name that? Do we name this Yeah, maybe like trifluoronitrogen or trifluoronitride. That's one way of naming it. Another way of naming it would be nitrogen trifluoride. Or some people might say, oh, this might be trifluoroamine. You call that an amine. Now, the situation here is when I look at ammonia, NH3, nitrogen trihydride, and I look at NF3, let's call this nitrogen trifluoride. So I have nitrogen trihydride, nitrogen trifluoride. They sound similar in name, right? But in terms of properties, I see something totally different here. This is not a good Lewis base. In fact, this is a very poor Lewis base. And in fact, it's a pretty poor Bronsted base as well. But why is that? Why is that one a good base? This one not such a good base? Yeah, exactly. Right. Right. The delta on nitrogen is not going to be delta negative. The delta on nitrogen is going to be delta plus. Yeah. So in this sense, this would have been better named trihydrogen nitride, because this is closer to nitride. In this sense, this would be better named nitrogen trifluoride, because it's more towards fluoride. And nitrogen would be positive. We can also see this in terms of oxidation states. What is the oxidation state of nitrogen in ammonia? Two ways you can do oxidation state. You can do oxidation state from the Lewis structure, or you can do the oxidation state from the formula. If you do it from the formula, you assign hydrogen first at +1. So we have 3 hydrogens at +1, that's +3. +3 plus what gives us 0? It's net charge. -3, yeah. And so this nitrogen is -3. This is, -3 is electron rich, electron poor? Electron rich. Now this is where you got to keep redox and acid base separate. We treat them totally separately because ammonium, if you recall this, Ammonium was electron rich at -3 on the nitrogen, and it's an acid. Ammonia is electron rich, but it's not an acid, it's a base. But look at the oxidation state. It's the same. So what do you think about the redox properties of these? Yeah, the redox properties are the same. Both of these are combustible. Both of them are combustible. Both of them are electron rich. Don't burn them though. Because if you burn ammonia or ammonium, you have the potential for forming oxides of nitrogen. And many oxides of nitrogen are toxic, like nitrogen dioxide, that brown, orange, brown. That was a beautiful orange smoke, is what they said in the video. I showed the Grand Camp video. The beautiful orange smoke is nitrogen dioxide. Nitrogen dioxide is toxic, so don't breathe this stuff. The person in the video said it has a real sulfury smell. It's not. I guess it's a sulfury smell. You know that there's no sulfur. You know, he was comparing it probably to oxides of sulfur, which are also toxic. Sulfur dioxide, kind of thing. But there's potential for forming oxides of nitrogen, like nitrogen monoxide, nitrogen dioxide, dinitrogen tetroxide, a bunch of these oxides of nitrogen, which are all pretty toxic. And so you don't want to burn this stuff. Or if you do burn this stuff, burn it inside the hood. Be safer. You're smelling that. But acid base, they're all on opposite ends, but redox are the same, or close to it, you know, just slightly different. Also, watch out, because if you burn ammonia in methane, you also have the potential for forming hydrogen cyanide gas. Hydrogen cyanide gas has the smell of burnt almonds, burnt almond. And so the characteristic smell of burnt almonds means hydrogen cyanide means danger. Be careful. All right, whereas over here, can you burn this stuff very easily? NF3, do you think that stuff's going to burn very easily? Ammonia, sure. You can burn that stuff. How about nitrogen trifluoride? No. In fact, what's the oxidation state of nitrogen in nitrogen trifluoride? +3. Yeah, maybe you could burn it, because what's the maximum positive oxidation state on nitrogen? +5. So yeah, maybe it has the potential of losing 2 more electrons, but it's not going to be a very good fuel. Not like ammonia or ammonium. That would be much better fuel. You know, this is already kind of burnt out. A little bit more to go. It's like, you know, carbon monoxide. You know, carbon monoxide, carbon's +2. Well, the max on carbon's +4. So carbon monoxide you can use as a fuel, but is it a very good fuel? You know, compared to, let's say, alcohol, gasoline, whatever. Is it easy to burn carbon monoxide? No, not that easy, but yeah, you can burn it and then get complete combustion. And so these little reference points are like, you know, like these little reference points are little like bits of knowledge that you can use for orientation, like, you know, gaining some kind of perspective. It's like if you move to a new area or new city or whatever, you need some reference points. Well, when you're talking about new numbers like this, you need some reference points to help orient yourself. You know, keep track of these things. Okay, let's take a break for 10 minutes. But before the break, I have to say, tomorrow I have to attend a funeral tomorrow, so I'm going to be absent. And so that means just you don't have to bother coming tomorrow. Just we'll come back and meet again on Thursday in the lab here. I'm not sure what we're gonna do. I'll probably just be able to make it up. You know, I know I'm behind, but I think I can make it up tomorrow. At least get done with chapter 15 and then started into 16. Okay. Not tomorrow, but Thursday. If not, then maybe I'll post a video or something to catch up, or have an outside session. We'll see. We'll figure out that. I need to take roll though, just to make sure everyone catches this. Started again here. So when we look at nitrogen trifluoride, this is not classified as an amine. It has a lone pair, but because of the positive charge density on nitrogen, it's not a very good electron pair donor. A good electron pair donor has lots of negative charge density, so it's willing to donate its electron cloud to another atom to form a bond. In this case, it's not going to happen. So here, this would be a poor Lewis acid. And we wouldn't classify this as an amine, so not an amine. These are good electron pair donors. They make good Lewis bases. For transition metal complexes, we can rank the Lewis bases according to atoms. And so Lewis base strength we say Lewis base strength and acid strength in general first. Is more complicated than Bronsted. And so it's not so easy to come up with a simple table like in Bronsted. We just have a ranking of acids, ranking of bases. For Lewis, it depends. A good base for one acid might not be good for a different acid. They're both Lewis acids, but some of the characteristics of that acid are different. And so to illustrate this, to really analyze acid-base strength, we use something called HSAB. HSAB, which we really aren't going to get into in this class, but let me tell you what it stands for. HSAB stands for hard, soft, acid, and bases. And the rule is pretty simple. The rule goes like this. A hard acid plus a hard base, this is good. Now that's a strong combination. However, if you take that same good acid, this is a hard acid, but if you take that hard acid plus a soft base, not as good. And so on the one hand, you might say, oh, that acid's good acid. But it depends on what base you're reacting with. Is that hard base or soft base? It changes. And so if we take that hard acid and we're reacting with a soft base, we wouldn't necessarily consider that a very good acid. It's not a good acid for the context of this reaction. Soft acid is much better for a soft base. So if we have a soft acid and a soft base, then this is good. But if we take a soft acid plus a hard base, is that very good? No. And so, you know, in Bronsted, it's like one size fits all. It works, you know, it works all the time, regardless. In this one, sometimes yes, sometimes no. You know? So what we're going to do is we're going to limit, you know. What we're going to do is we're not going to look at the entire universe of Lewis acid-base reactions. We're just going to pick a small galaxy of those, which would be the transition metal complexes. And with transition metal complexes, if we're only dealing with one type of acid, that is a transition metal, then we can rank the bases according to that one type of acid. But even that one type of acid can vary. This is not as good. And so let me talk about the origin. This is hard soft acid base theory. This is based on quantum mechanics. So this is kind of a simplified, version that you don't have to do bucket loads of calculations. You know, it's just simple. And what it boils down to are things like polarizability. Do you recall polarizability? Electron cloud polarizability. You know, soft is more polarizable than hard. You know? And so one way of thinking about this is let's look at some orbitals. Let's look at a 2p orbital. So if I have a 2p orbital, you know, and let's compare it to a 4p orbital. What's one difference between a 2p orbital and a 4p orbital? Bigger, yeah. It's like 4 times bigger. So if you have 2 electrons, let's say in a 2p orbital versus 2 electrons in a 4p orbital, there's going to be a difference in terms of polarizability. Polarizability is how easy is it to distort the electron cloud? You know, how soft is it? The more polarizable it is, the more soft it is. And so which one are these? You know, these 2 electrons in 2p are more tightly held, tightly bound than these. You know, this is a big orbital. The big orbital, you know, the electrons are more free to roam. And therefore, what we say is like a 2p orbital is a much harder orbital than a 4p. 4p orbital is a much softer orbital. And do you guys remember LCAO? LCAO, another acronym. HSAB is not taught or discussed in the book, but you can look at it in Wikipedia or something like that. LCAO is discussed in the book. What was LCAO? LCAO was part of which bonding theory? Or what were the 2 bonding theories, if you recall? The 2 bonding theories, there's actually only one bonding theory, but one's just a simplified version. Yeah, exactly. Valence bonding and molecular orbital. Valence bond, an orbital's, well, an orbital overlap forms a bond. And so we take an atomic orbital on one atom, an atomic orbital on another atom, and overlap them, we get a bond. And so we retain the atomic orbitals and just overlap them. In molecular orbital, what happens is LCAO. LCAO stands for linear combination of atomic orbitals. Linear combination of atomic orbitals. Yeah. This is a part of HSAB. This is a little bit more of the origin of HSAB. So what happens is this. When you do a linear combination of atomic orbitals, you take atomic orbital from atom A and atomic orbital from atom B, and you mix them quantum mechanically. That is, you combine them quantum mechanically. When you combine those orbitals, you might remember doing something like this, where you take atomic orbital from atom A and atomic orbital from atom B, and you do LCAO. When you do an LCAO, you generate something called a bonding molecular orbital for AB. This is going to be an MO. And at the same time you create a bonding MO, you also create an anti-bonding MO. So this would be the anti-bonding MO, which we'll call MO star. Do you remember doing these? For example, sigma 2p star, pi 2p star. This is LCAO. And so when you do a linear combination, like if you take a gigantic 4p orbital and you do an LCAO with a tiny 1s orbital, you know, you're taking this gigantic orbital and a tiny orbital and you're doing an LCAO. And that LCAO, you're taking something that's quite big and soft and combining it with something hard. It's not going to form as stable of MOs as something like this. Like say, instead of, if you took like the 1s and the 2p, that would make a better LCAO. And so how that manifests itself is like this. The MO becomes more stable, you know? And so if you have soft, hard, you know, it becomes more stable. And the antibonding at the same time becomes less. But antibonding is, like the name implies, not good for bonding. And so, you know, you got good combinations of atomic orbitals, which leads to stable molecular orbitals. So, and so this, you know, you take the quantum mechanics of this, and then you try to come up with a simple picture. And the simple picture is this hard, soft, gas, and base, to try to help us understand the ranking of acids and bases in terms of their reactivity. And then we take it case by case. You can't always say this is a strong acid under all circumstances. You know, it depends on what you're reacting with. And so this is why Bronsted is so appealing. You know, Bronsted is so appealing because you got a chart there. You know, are you going from stronger to weaker? It's simple. You know, this is just more complicated. So I'm just going to leave it at that. You know, Lewis is more complicated. If we want to better understand Lewis, then we need to put things into the perspective of MO theory, see what kinds of molecular orbitals are formed, what makes a good MO, you know, those kinds of things. And HSAB is trying to help us simplify that, you know, by better visualizing the reactivity of this type of stuff. But for transition metal complexes, we can come up with a ranking. And so for transition metal complexes, we could have some harder acids and some softer acids. So something like this, you know, although this is not a transition metal, right? This is a main group. As a transition metal, I'll use it kind of loosely because we aren't restricting it. Just metal ion complexes. They say transition metal because most of them are transition metals. So if we have something like aluminum 3+ versus Na+, which one would make a better Lewis acid? Which one do you think? Which one would have a better attraction for that negative charge density? You know, the lone pair, better able to accept it. Aluminum 3+, you know, why? Because the charge and the size. It's a very small ion. Small, high charge density. This is very poor. And so it's so poor, it's considered like neutral in terms of Lewis. Sodium, yeah, Na+. This is pretty good, you know. It's not a transition metal, though. We can look at a transition metal here. Let's look at calcium 2 plus versus Pb 2 plus. Pb is a heavy metal. Do you think heavy metals are soft on the soft side or the hard side? What would your guess be? Soft? Yeah, more orbitals, more electrons. They're soft, you know, like lead, 82 electrons. That's a lot of electrons. I talked about lead before, didn't I? A lot of electrons, a lot of orbitals. It's good at absorbing what? Light, you know, X-rays. Did I mention that? I guess I talked about that in the morning class. You know, you got a lot of electrons. You can absorb a lot of light. And so, if we want an X-ray shield, we want something with a lot of electrons. And hopefully those electrons can absorb X-ray photons, you know, X-ray. And so lead is good. Actually, there's things with more electrons than lead, right? And so what has more electrons? Lead has 82 electrons. Let's go to polonium. Polonium has 84 electrons. That would be even better. But the problem with polonium is, you know the problem with polonium? It's radioactive. So if you're trying to protect yourself from X-rays and you're using radioactive shield, it's not very effective. In fact, most of the elements past lead are radioactive. Bismuth is too brittle to use. Lead is much more malleable, so you can form sheets. Like you go to the dentist, they threw a lead apron on you, you're good, or lead whatever. And so lead is going to be the kind of the most stable, the easiest to work with the most electrons. However, lead is heavy metal, and heavy metal lead to heavy metal poisoning, which isn't good. But it's good at shielding you from electrons. What's good as an X-ray window? As an X-ray window, you want the least number of electrons. And so one time, I have a friend that works at JPL. And he was asking, he bought a whole bunch of surplus vacuum equipment, which looks like stuff off a submarine. One of the things had a window where you could shine X-rays in as a sample. And the window was made up of beryllium. You know, beryllium is structurally strong, and it's got very few electrons. It's very lightweight. In fact, do you know beryllium? A very small atom. And the beryllium 2 plus ion is tiny. Beryllium used to be used in aerospace quite a lot, you know. Like, you've heard of, like, magnesium. Have you heard of magnesium wheels? People like real magnesium wheels because they're so light. They're lighter than aluminum wheels. So if you have like the old term mag wheels came from magnesium. They actually use magnesium. Of course, if it got hot enough, it could burn, you know, because all metals are electron rich, but flammable potentially. It's the same thing with aluminum. It can burn. Once I was over at, this was when I was like in junior high school. I saw this car catch on fire. And I thought, you know, it's metal. It's not going to really burn. And it burned. It was just surprising how much of it burned. It was a fancy sports car. But anyway, so he had a bunch of beryllium windows. Beryllium windows were used for X-rays. You know, you want few electrons if you don't want light to be absorbed. But the problem with beryllium is, I had already known this, beryllium was heavily used in aerospace as lightweight structural material. But all the machinists that used to machine the beryllium ended up dying. You know, they all died from the same disease. And what it was this. Beryllium ions, which are tiny, are very reactive. And so we need magnesium ions and calcium ions in our bodies. Magnesium ions and calcium ions are a lot bigger. Actually, beryllium is even tinier, so I should make this bigger. Magnesium 2 plus and calcium 2 plus. And so what happens is the beryllium knocks out the magnesium, knocks out the calcium, substitutes for it, and binds so tightly it doesn't let go. You know? And so it screws up a lot of your biological magnesium and calcium. And so that caused a lot of problems. So anyway, I didn't take him up on his offer. He wanted some storage space in the garage. But getting back to this, we would certainly say that lead is soft. What about calcium 2+? What would you say about calcium? Calcium 2+ for sure will be a better base than sodium ions. Sodium ions, no good at all. You know, it's no good at all because it's low charge density. It's not like beryllium. Beryllium would be probably pretty good, you know, but we don't want to work with beryllium. Nobody wants to work with beryllium. So would you say calcium's on the soft side or the hard side? Hard, yeah. Calcium's on the hard side. So those are some acids. Normally the higher the charge, the smaller the size, the better the acid is. But there are other factors, you know, because other factors that come into play, like hard, soft, etc. But let's take a look at the bases. You know, the bases in Lewis acid-base reactions are often called ligands. You know, these are just Lewis bases, so two different names for Lewis bases, ligands or bases. And it turns out that carbon donors are the best Lewis bases.
So for the transition metals, are we ranking them like based on their electronegativity?
No, based on charge and size. Charge and size, not based on electronegativity. Yeah. Size is related to electronegativity. The smaller the size, the more electronegative it is. But metals, you know, let me ask you this. What's the electronegativity of fluorine? Do you know the number?
No, we don't.
Anybody know the number? 4, yeah. Fluorine's a 4.0. What's the electronegativity of fluoride? Is fluoride a 4.0 also? No. In fact, fluoride doesn't even want an electron at all. Fluoride, it's already maxed out. Where's it going to put an extra electron? You'd have to put an extra electron in the next higher energy shell. That's going to be highly destabilizing. No, it's not going to be favorable at all. And so its electronegativity drops off a cliff, basically. It's way down here. It doesn't want an electron. It's like a noble gas. You know, for example, how electronegative is neon gas? Does neon want an electron? Not at all. I mean, neon's already got a filled shell. Well, so does fluorine. And so this is like Nobel gas, like electronegativity. But what if I had something like F+ with a positive formal charge or a positive oxidation state? What would its electronegativity there be? Maybe you'd think so, because, you know, F+ would be like oxygen, but there's a big difference. Oxygen only has 8 protons. Fluorine has 9 protons. Same number of electrons. It's going to be much more electronegative than oxygen. In fact, this is going to be much more electronegative than fluorine. This is going to have electronegativity greater than 4.0. Probably significantly greater than 4.0, because, you know, fluorine was already the most electronegative, and then you throw a positive charge and make it lose an electron, it's going to make it much worse. This wouldn't happen, though. Fluorine with a positive formal charge, this doesn't happen with It's way too electronegative for that. But if you did, it would be terribly unstable, something like this. So for the metals, it gets complicated, you know. It is related to electronegativity, but it's not the electronegativities that you read off the tables. It's electronegativity. If you read the electronegativity off the periodic table, aluminum is way down there. It has a very tiny electronegativity. The reason is metals are electron rich. Metals want to get rid of electrons. Metals don't want to take an electron. And so if we look at the electronegativity of aluminum, it's low. You know, the lowest would be over here about 0.7. So it's quite a bit low. However, aluminum 3 plus is high. You know, this has a much higher electronegativity. And so I would say, yes, we could use electronegativity, but not in the sense that you're used to using. You don't read them off the periodic table. You have to analyze them one by one. And so, for example, iron 2 versus iron 3. Iron 3 would have a higher electronegativity. You know, what's that number? That number we'd have to guess or figure it out quantum mechanically. Rather than using electronegativity, I like to use charge density, because there we don't have to have a number, and there we don't get confused with the electronegativity table here. You know, in Chem 4, Chem 1A, I get this question a lot. A lot of people get it mixed up. You know? They think fluoride is 4.0. Fluorine with a positive charge is still 4.0. It's always 4.0. Fluorine, it's not the case. And so in terms of charge density, this is the way I'd look at it. In terms of charge density, this has a much higher charge density. It's very small, high charge. It's going to pull electron density towards it. That means it has great electronegativity. It's true. So this one has greater electronegativity than this one. You know? Okay, so let's see. So as far as the best Lewis bases are carbon donors for transition metal complexes, followed by nitrogen donors, followed by oxygen donors, followed by halides. And so this is the way it works. Let's give some examples here. So examples of carbon donors would be carbon monoxide. If you look at this, which one looks like a better candidate for donating an electron pair? We have oxygen versus carbon. Which one looks better? Normally you'd say oxygen. You know, oxygen is more electronegative, right? And so it should be, this shouldn't be a carbon donor. This should be an oxygen donor. It should be better. But take a look at the formal charges on this. What are the formal charges on carbon and oxygen here? This carbon has 1, 2, 3, 4, 5 electrons. How many should it have? 4. That means it gets... And this oxygen has 1, 2, 3, 4, 5. That means the oxygen is positive, but this can't be right. Oxygen is more electronegative than carbon. Oxygen should get the extra electron, not carbon. So let's get rid of that formal charge. If we get rid of that formal charge, what I'm going to do is I'm going to take this lone pair from carbon. Actually, I'm going to do, what am I going to do? Well, let's do this. Let's just make this a double bond and then give oxygen that lone pair back. We have this. Now look at the formal charges here. I have 1, 2, 3, 4 on carbon, 0, and 1, 2, 3, 4, 5, 6 on oxygen, 0. So both of the formal charges are 0 here. So, is this structure better? No, this structure is actually worse. What's the problem with this structure? Do you see the problem with this structure, the bottom one? Yeah, this is a violation of the octet rule. And so we need that octet. And the only way to get that octet is to have this weird formal charge situation. Once we generate this weird formal charge situation, this makes this carbon unusually reactive. And so this is a very strong Lewis base. It's a carbon donor, carbon monoxide. Another carbon donor would be this, cyanide. In cyanide, once again, in order to get the octet, we have to throw a negative formal charge on the carbon. And cyanide, the nitrogen's 0. Cyanide is a net -1 charge on the anion. And so, very strong donor. As far as nitrogen donors go, we have the amines, like ammonia. That's a very good Lewis base. And the amines. As far as oxygen donor goes, we have hydroxide. If you think about hydroxide versus ammonia, which one is a stronger Bronsted base? Hydroxide. Hydroxide is a strong base, ammonia is a weak base. But in terms of Lewis, it turns out that ammonia is a stronger Lewis base for metal cations than hydroxide. And that has to do with, MOs and all that quantum mechanical stuff, which we aren't going to get into. We're just going to kind of brush it aside. Water is another one that's common. Water we call aqua. We get these names. The names we give them as ligands, this would be called carbonyl, not carbon monoxide, carbonyl. Cyanide would be called cyanido. Ammonia is called amine when it acts as a ligand or a Lewis base. Now, note, this amine has a different spelling than this amine. If I have an amine spelled with 2 M's, amine spelled with 2 M's means ammonia. Amine with 1 M means ammonia-like compound, like methylamine, dimethylamine, trimethylamine, etc. There are a bunch of them. This oxygen donor, hydroxide, is called hydroxido. The water is just called aqua. Halides would be like chloride, bromide, iodide, fluoride. These all have multiple lone pairs. One of them can donate. We don't have more than one lone pair donate. So in this case, only one or the other. We can't have both these donate because they're on opposite sides of the structure. Over here, just one of these 3 donate on hydroxide, and only one of the 2 donate on water. One of the 4 donate with these. We don't call chloride anymore. We call it chloro. This is called bromo. This is called iodo. But, these are examples of what we call monodentate ligands. Monodentate. Monodentate means we only have 1 atom that donates per base. Let's look at another nitrogen donor that has 2 atoms. And so this would be ethylene diamine. Ethylene diamine looks like this. It's going to be H2N, CH2, CH2, and H2. So we have a lone pair here and a lone pair here. And so what can happen with ethylene diamine is one lone pair can bind, and then the molecule wraps around and the second lone pair binds. And so let's take a look at something like platinum. Platinum 2+ is our Lewis acid. And if we have an ethylene diamine attack that, usually what we say is the base attacks acid. So one of these binds there. And so what we end up with is a platinum like this with an NH2 bond. Now the lone pair is being used as a bond. CH2, CH2, and then the NH2 here. And what we call this is we call it a bidentate ligand because this second nitrogen can wrap itself around and then bind to the platinum here. And if that happens, we end up with something like this. This platinum is still 2+. We end up with a platinum 2+ here, and then NH2. The lone pair is being used as a bond. CH2, CH2, NH2. And now this nitrogen is bonded. This is called a coordinate covalent bond or dative bond. Both bonding electrons come from the nitrogen itself. So this is a bidentate ligand. It's also a nitrogen donor, so it's a pretty good Lewis base. And this is the most common bidentate ligand. There's another bidentate ligand that's an oxygen donor. And so let's take a look at that one. Next. It's oxalate ion. Oxalate ion is C2O4 2-. If we look at the structure of oxalate, it looks like this. There's two back-to-back carboxyl groups. Carboxyl is COO- groups here. So we have a negative formal charge on this one, a negative formal charge. Actually, because of resonance, these two bonds are the same. They're 1.5 bond order, and the negative charge on both oxygens are the same, -1/2. But we'll keep it like this. Which one do you think will be a better donor? The oxygen with the negative formal charge or the oxygen with no charge? I would expect the oxygen with negative charge to be better, just because it should be a better donor sense compared to this. But in reality, these two oxygens are the same. And so we'll take a look at oxalate next. Let's take a break now. Then we'll start up again right after the break. So another very common bidentate ligand is oxalate, but when we treat it as a ligand or Lewis base, we call it oxalato. And so when we have anions like this, we use the O ending, and so chloride, chloro, oxalate, oxalato, or oxalato. And this is going to be a bidentate ligand. The oxygens with negative formal charge should be better, but really all the oxygens are the same. And so we have like these two combined, and these two can be on the opposite end. You know, if we had this oxygen bind and this oxygen bind to the metal here, what that creates is a 4-membered ring. If you look at this, we have the metal, oxygen, carbon, oxygen, a four-membered ring. Over here, if you look at this one, we have the metal, nitrogen, carbon, carbon, nitrogen, metal. That's a 5-membered ring. Now, 4-membered rings are highly strained compared to 5-membered rings. We can look at this based on simple carbon rings. And so if we take a look at some carbon rings like this, a 6-membered ring is no problem, so we can have something like this. This is called cyclohexane, which would be a 6-membered ring. 5-membered ring is no problem too. When you look at these carbons, do you know what the hybridization of this carbon is? Can you tell what the hybridization, like sp2, sp3, etc.? sp3. These are sp3 carbons. sp3 carbons are what geometry? Shape. Tetrahedral. And what's the bond angle for tetrahedral? 109. Or 109.5 or 109.47, depending on how many sig figs you want. But 109, most people say. So if we had a ring like this, CH2, 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 CH2. This one is cyclohexane. This one's called cyclobutane. But means 4 carbons. If we look at cyclobutane, what do you think the angle should be in the ring? So if I look at this ring, the angle should be, if it's a 4-membered ring, it should be a square. And the square would have what angle? 90 degrees. What's the hybridization of this carbon? It's also sp3. And so the normal angle for this, is a carbon with 4 bonds. Carbon with 4 bonds should be sp3, 4 separate single bonds, let's say, sp3. The angle should be 109, so this angle is highly distorted. It should be a 109 angle, it's a 90. That means poor orbital overlap. If you think in terms of valence bond, the orbitals aren't coming straight on. They're coming at an angle, and they aren't overlapping in the meaty part of the orbital. So this is unstable. 4-membered rings are unstable. 5-membered rings are okay. What about a 3-membered ring, like CH2, CH2, CH2? This is cyclopropane. Cyclopropane is potentially explosive. Why? Yeah, the angle's 60 degrees. That's highly strained. The normal angle on that should be about 109. And so this is very unstable. So when I look at this, this doesn't look good. This looks highly unstable. So it's not bidentate with these 2 oxygens here. And so this can't be right. Instead, it's got to be these 2 oxygens here. So if I have this lone pair come here and this lone pair come here, then what would I form? I'd form a 1, 2, 3, 4, 5-membered ring. 5-membered ring aren't highly strained, and so these could be relaxed. And so this has got to be a bidentate with these oxygens here. Now, could it be a tetradentate? Tetradentate would have 2 more oxygens. It can't, because these are, you know what the hybridization on this carbon is? Yeah, this is sp2, trigonal planar. And so these oxygens here are on the opposite end of this ion. So these can't bind to the metal, because they're pointed away from the metal, not towards it. And so that would be a bidentate. We can actually put 2 bidentate ligands on there. So let me give you an example of that. An example of that would be something like this, where we have a platinum with 2+, and then we stick on 2 of these oxalatos, like this. each of these oxalates are 2 minus. And so if this is 2 minus, this is 2 minus, and this is 2 plus, what's the net charge on this? The net charge here would be 2 minus. Okay, let's look at some other bidentate ligands, potentially. So here, let's try methylene diamine. Okay, if I try methylene diamine, it has 2 means, but in this case it has a methylene, which is just 1 carbon. Here. Would you expect this to be bidentate or monodentate? So what we'll do is we'll put a metal here, and if this lone pair binds here, do you expect the second lone pair over here to bind as well? Why or why not? So if one lone pair binds, will the second one come in and bind? That's the question.
No.
And that's correct, no. And the answer is? Yeah, because it would form a 4-membered ring. If the second one bound here, we'd have metal, nitrogen, carbon, nitrogen, metal. It's a 4-membered ring, highly strained. And so it wouldn't be stable. So the answer here is this is not bidentate. This would be monodentate. Okay, try propylene diamine. Propylene diamine would have 3 CH2 groups in between the NH2s. And I'll be right back in just a second.